I'm Robert, and this is Philip, and we're going to tell you about a project we've been working on in the RISE lab at UC Berkeley. It's called Ray. We've been building a system called Ray, which is a distributed system for AI applications. And it's not just the two of us, we've been working with a large group of collaborators. So one natural question is, why build a new system? Well, the two of us, so our background is in machine learning, and over the past several years, we've been working on designing better algorithms for optimization and reinforcement learning. And so every time we'd come up with a new algorithm, we'd want to try it out to evaluate it empirically. And these algorithms are often computationally intensive. And so that means distributing the computation over a cluster. So we've used a lot, over the years, we've used a lot of different frameworks and tools for distributed computing. But every application that we worked on had slightly different requirements. And we often ended up needing more flexibility than the different frameworks offered. So this may come as a surprise, but a lot of machine learning researchers largely ignore existing frameworks and build their own custom systems for every application they're working on. And this is, as a result, they spend a lot of time engineering. Even if the application they're working on has a fairly simple computational pattern, going from a prototype on a laptop to running efficiently on a cluster is often engineering intensive. And so we'd like to simplify that process and make it easier to distribute computation over clusters for AI applications, especially for reinforcement learning. So to understand what the requirements of such a system are, it's important to understand how machine learning applications are changing. So today when we think of machine learning, we think of supervised learning. You take a data point and apply a label or make a prediction about that data point. And this has been a big success story in machine learning. But going forward, a lot of the applications that use machine learning will use machine learning not just to make and serve predictions, but also as components of policies that operate in dynamic environments and take sequences of actions and make sequences of decisions. So the kinds of applications that I'm talking about are things like dialogue systems, where an agent goes back and forth in conversation to accomplish some goal, or healthcare, where we may have health recommendations pushed to us in real time based on our activity, or we'll have personal assistants that give us context and advice based on our sensory input. And similarly, in robotics applications and autonomous driving applications, sequences of decisions and actions are required to run the application. So the point here is that there's a paradigm shift in the kinds of ways that machine learning is being used in real applications. And we're going from a world where instead of making just one prediction, we'll make sequences of actions. Instead of operating in static environments where we assume that the distribution during training is the same as the distribution during testing, we'll be operating in dynamic environments where the actions we take actually change the environment. And instead of getting immediate feedback or rewards about whether the label that we applied to a data point or the prediction we made was correct or incorrect, we're moving to a setting where rewards are more delayed. And for instance, a dialogue system may not know whether something that it said at the beginning of the conversation was worked out or not until it gets to the end of the conversation. So the changing nature of these applications motivate different system requirements and different algorithms. And Philip is going to tell you more about these algorithms.
OK, so we prepared a cool demo, which is going to train some a robot, simulated 3D robot, to walk. And running this on a laptop would take around more than 2 days. And so we are going to try to train this on a cluster with 20 nodes and 800 cores, which makes it train in about 15 to 20 minutes. So I'm going to start it now, and then I'm going to talk a little bit more later about how it works and see the results. OK, so here we are logged into a cluster. And I'm going to start the training of the single node version here. And then the cluster version is being trained here. And OK, so how do And by the way, this is using a stochastic algorithm, so some of the runs don't work, so we will see at the end if it works or not, so no promises. How do the application patterns in reinforcement learning influence the design of our system? The applications need to process inputs from very different sensors, and they need to be processed in parallel and also in real time. We then use the sensory observation to perform a large number of microsimulations, and that allows us to determine actions. So here are a few examples. On the left, you see an Atari game where the observations would be the pixels on the screen. The actions would be what we do on the joystick, if we go like left, right, up, down, or press some buttons. And the goal of the reinforcement learning agent is to beat the game. In the middle, you see a simulated robot, and there the observations would be the angles of the joints of the robot, and the actions would be torques of the robot. And simulations are just trial runs of the robot that tell us how well the policy is doing. And then on the right-hand side, you see a Go board. So recently, DeepMind had some good success in beating the world champion in Go, and there the state or the observations would be the state of the board, and the actions would be to place new stones on the board. These simulations are then used for learning a so-called policy, which is a mapping from the observations to the actions. So how this works is we can do a number of simulations, and then some of them are going to finish first, and then we can already update the policy using these. And then maybe some others, we can launch some more simulations and update more of the policy and so on in asynchronous fashion. Often, this policy is learned, it's represented by a deep neural network. And so we use typically TensorFlow to implement that. And another requirement is that most reinforcement learning algorithms and the infrastructure for reinforcement learning is often developed in Python. So these could be simulation interfaces, or it could be the learning interfaces themselves. And so it's very important for us to support Python really well. OK, so how do these application requirements translate to the system requirements? The system needs to be able to support dynamic task graphs. And each of the tasks that gets executed will probably take a different amount of time. So for example, for simulations, the robot might fall down pretty quickly, and then we just terminate that simulation. And another simulation might be successful, and that takes a longer time, for example. Typically, also, each of these tasks does a different computation. So some of it might be simulation, some of it might be doing search, another one might be evaluating the policy, and so on. And so we need to support heterogeneous computation. Some of it might run on a CPU, some of it might run on a GPU, and this all needs to be supported. Also, to learn the policies, we need to do hundreds of millions of simulation steps. And so we need to be able to schedule billions of tasks per second. And then last, we also need to make it easy to parallelize existing Python implementations of reinforcement learning algorithms.
So now I'll describe the API in a little more detail and the abstractions that we're exposing. So one of the core abstractions is the ability to take an arbitrary Python function, such as one of these toy examples, and designate it as a remote function. And when you do that, now when you call one of these remote functions, instead of blocking while the task is executing, the function call immediately returns a future or an object ID, and a task is then created that is scheduled somewhere throughout the cluster. And so here, this is an example script where we're calling three different remote functions. It creates a computation graph which looks something like this. You can see that the two calls to the zeros function can be executed in parallel, but the dot function, that task has to wait for the previous two tasks to complete because it uses their results. And the way we're encoding, because we're passing ID1 and ID2 into the third function, that's how we're encoding gives rise to the dependencies in the computation graph. And when you actually want the results of the computation, you can call ray.get to block until the computation has finished and retrieve the results. So this is already about half of the API. That's enough to take a lot of existing code and parallelize it efficiently. One thing it doesn't do is enable you to share mutable state between tasks. And that's actually an important use case because in machine learning, a lot of computations are very stateful, whether that state is in a neural network or in some environment that you're interacting with or something else. Here, these remote functions are essentially stateless. They map inputs to outputs but don't share mutable state with each other. The way we achieve that here is through an actor abstraction. So here's a Python class with a method for incrementing a counter. And the 3 calls to that method all share and mutate the state of the counter object. And of course, this is a toy example. So how would we translate this into the distributed setting using Ray? Well, we would designate the class as a remote class. And then when we instantiate the counter object, that would create a new actor process somewhere in the cluster. And then method calls turn into tasks that get scheduled on that actor and return futures like before. So the computation graph for this short script here would look something like this. The thick arrows indicate that the method calls all share the state of the counter object. And here, the different method calls can all mutate the state and share the mutable state with each other. So the cool thing here is not that these aren't 2 separate parts of the API. You can either use actors or use remote functions. They actually interoperate seamlessly in the same computation graphs, in the same scripts, the same workloads. So you get the benefits of traditional data flow, stateless data flow systems, as well as actor frameworks all together in the same script. And one thing just to mention is you can specify resource requirements like GPUs with syntax like this. Okay, so now I'm going to tell you a bit about the architecture. So here's a depiction of a cluster with 3 machines. And we have drivers and workers throughout the cluster. These are Python processes. And these should be thought of as like Spark drivers and Spark workers. The workers will execute tasks. On each machine, there's a shared memory object store, which allows the different worker and driver processes to read the same objects through shared memory. And that's important, especially in the large multi-core setting, where you may have hundreds of workers on the same machine, and you don't want them all to have their own copy of the data. You also don't want them all to have to serialize and deserialize the data. So here we store objects in the object store using the Apache Arrow data layout, which dramatically reduces the amount of time required for deserialization. One other process that lives on these machines is the local scheduler on each machine. Again, this is an optimization for the large multi-core setting. And here, now whenever a driver submits a task, it submits it to its local scheduler, which can then assign it to a worker on the same machine. In contrast with Spark, workers can also submit tasks which are then assigned to other workers. And this is, in terms of the API, when a worker submits a task, what that would look like is basically one remote function calling another remote function. Now, assigning tasks, handling tasks locally on the same machine can be great for latency, but if the load is much higher on one machine than another machine, you need to balance these things across the different machines. And we have a replicated global scheduler for that. And local schedulers, if they're sort of overburdened, can pass tasks along to the global scheduler, which can then rebalance it across the cluster by assigning it to the local scheduler on another machine. So this is a bottom-up distributed scheduling approach. And this is in contrast with systems which have centralized schedulers, which can sometimes be scalability bottlenecks. Another key feature of the system is the global control store, which attempts to take all the metadata and all the state out of the other components of the system, out of the schedulers and things like that, and centralize it in a single sharded database. So now, and the motivation for this is actually simplifying the design of the system, making it easier to develop and debug and things like that. So to give an example, because the other processes are largely stateless now, if one of them fails, it can be restarted and read the up-to-date state from the global control store. And similarly, it helps with scalability because the global schedulers are stateless, they can be replicated more easily. The global control store also serves as a message bus for communication between the different processes, and as a point of contact for building debugging and profiling tools. So to illustrate why this is such a natural fit, because all of the state and metadata of the system is in this database, you can easily build profiling tools because you can just query the database during runtime as the system is running. And so that is, you don't, instead of having to have a web UI which has to send messages to all the different processes in the system, it can just communicate with the global control store. So these are sort of the three central features of the system: the shared memory distributed object store, the bottom-up distributed scheduler, and the centralized control state of the system. So now Philip will tell you more about performance.
So let's now talk a little bit about how this architecture allows us to achieve the kind of performance requirements that we set down earlier. In this graph, you see a scalability plot. On the x-axis, we plot the number of nodes. It goes from 1 node to 50 nodes. And then on the y-axis, you see the number of tasks that are done per second. And as you see, on 50 nodes, we can get up over 1 million tasks per second. And then so that's for the throughput. And then for the latency to submit a task to the local scheduler and then let it be executed by the local scheduler is around, oops, I think the Wi-Fi might make problems. It's around 300 microseconds. And submitting a task to another remote machine and executing it, so this is a no-op task, is around 1 millisecond. Here's another plot that shows the fault tolerance capabilities of Ray. So on the x-axis, you see the time. And then we plot the number of machines in dashed red. So it starts off with 20 machines up here. And then after like 25 seconds, we disconnect one of the machines. So we have 19. And then after like 50 seconds, we disconnect 9 more machines. So we have 10 machines here. And then we reconnect all the machines again. And so what is interesting here is the task throughput. So it starts off at around 500 tasks per second. So that's dictated by the workload. And then after the first machine got disconnected, we need to reconstruct the machines. We do lineage-based fault tolerance. So we need to reconstruct the objects that were on that machine. So we have a dip here in the number of tasks that get processed. And then the same after we disconnect half of the machines. And then the system operates normally after that time. And then when we bring the machines up again, then it goes back to the original throughput of 500 tasks per second. OK, so let me now switch to the example that I started earlier on the cluster. And let me give you a little bit of background on what this is about. So this is a cool new algorithm that very recently came out of OpenAI. It's called Evolution Strategies. And it's an optimization algorithm for training reinforcement learning agents. So how it works is, the goal here is to train a humanoid 3D robot to do walking in simulation. So we have two components. One of them is the simulator. The simulator can take as input actions, which are talks on the joints. And then it will simulate one time step, and then output observations of the next time step. And these observations are then fed into the policy. The policy is a neural network of a few layers implemented using TensorFlow. It takes as an input these observations and then computes the actions that are fed into the simulator in the next state. And the simulator also outputs rewards. And the reward is capturing the problem that we want to learn. So for example, in this case, we want to learn walking. And then the reward is just the sum of the forward velocity over all time steps. So what the algorithm does is, it starts with an initial random policy, and then it applies a bunch of perturbations to that policy. And then it tries out all the perturbed policies, runs the simulator to get the reward, and then according to how much reward the policy gets, it combines all these policies into a new big policy, and that is going to do better in the next iteration. So how does this look like in pseudocode? First, I'm going to present the serial implementation. So we have a worker class here, which holds the simulator and the neural network. And it has one method, do simulation, which takes as input the policy and then a seed for the perturbation that is going to be applied. It generates random numbers from the seed, applies it to the policy, and then tries out the new policy with the simulator and returns the reward. We then create a number of these workers, in this case 20 workers, and we also create an initial policy, which is just random. And then we run the main loop of the algorithm. So we do 200 iterations. We generate a number of seeds for this particular iteration. And then we we do the simulation on each of the workers and collect all the rewards and put them into the function that computes the new policy for the next iteration. So how would we parallelize this algorithm using Ray? We would put this at ray.remote decorator that Robert introduced earlier. This makes the worker class into a remote class. And then we can instantiate a number of these workers, and they will be instantiated either on the same node in a different process or on a different node. We can then do these simulations in parallel, and this will be executed in the background and will immediately yield a future of the result. And so these will all be executed in parallel, and then we can get the result of the future. So this will block until all the results have been computed, and then will yield the actual returns. OK, so let's now see how the training is doing. So that's back on the cluster. This is the single node version, and this is the cluster version. And we can now download the policy and visualize it. OK, so on the left-hand side, we see the single node version. And on the right-hand side, we see the cluster version. So unfortunately, the training here was not quite long enough and that it could learn its stable walk. But the cluster version already looks better than the single node version is just falling over right away. And the cluster version can at least balance a little bit. So let me show you how we can train this actually. Let's see. All right, I think I'm disconnected from the network.
That's fine. There's you have it on in your downloads.
OK, is this good enough?
Do it from your downloads.
OK, yeah. OK, so this is the same problem, trained with a slightly different algorithm called policy gradient. It's also implemented on top of Ray. It's a little bit more complicated than the one that I showed. But this is how it learns to walk. So this is after 100 iterations of the algorithm. It already makes a bunch of forward progress. And then after 200 iterations, the walking is already pretty stable. And then after 500 iterations, it actually learns a pretty nice run. OK. So now let me switch to the PDF version of the presentation.
Yeah, full screen. Full screen.
Yeah. Oops. OK, it's unfortunately on the wrong side of the laptop. OK, maybe this is good enough. OK, so this slide shows how the evolution strategies implementation of Ray is scaling. So we are comparing here against the reference implementation that was released by OpenAI. And as you see, for a given number of nodes, we can do more simulation steps than the reference implementation, which is a specialized system, a specialized distributed system for this particular algorithm. And also, we can scale up to more nodes. It was also way easier to develop this. So the number of lines of code is about half of what was required for the reference implementation. And we could implement this in a couple of hours. Okay, so let me now talk a little bit about the relation between Ray and Apache Spark. So we view them as complementary. And Spark you would use for things like data processing, ETL things, running SQL queries, and things like that. Ray, you would, and also using more classical machine learning, using, for example, MLlib. And Ray you would use for running reinforcement learning algorithms. And we could, so this is not done right now, but we plan to make it so that both systems can interoperate through the object store. And Apache Arrow would be a common format that both systems can use to talk to each other. So to summarize, Ray is the system for AI applications. It's available open source on GitHub. And you can, we also have a version 0.1 release, so you can install it using pip install. And if you have some application that you would like to try out, please get in contact with us. Thank you.
Thank you so much, Ray and Robert and Philip, for an excellent presentation. This was really exciting to see. We have time for maybe 1 or 2 questions, and then we are breaking for lunch. Please raise your hand up, and I'll.
My question is related to your simulation. Is that the physics engines that you use to calculate the person's movement? Because my point is that usually for reinforcement learning, you need to actually try it out in the reality so that you can learn from the reality. So I'm just wondering that, are you learning your simulation in this case? What are you actually learning?
Oh, your question is whether we are also learning the simulation or if you use a simulator that already exists? Is that the question?
Yeah, so for example, like you're simulating the reality, right, in your examples, right?
Yeah. So we use an existing physics simulator called Motoko for the simulation. And so we set up the robot, and then we use the simulator to simulate the robot. What we learn is the policy, and that is what the robot does as a function of the input of the joints and so on of the robot. Does that answer your question?
Okay.
Thank you. Anyone else?
Thanks for the talk, and I love the animation. So Robert did mention that Ray enables sharing mutable states, but how do you implement that, and how do you implement the distributed consensus, or maybe in reinforcement learning scenario, distributed consensus is not really important?
So how do we implement distributed consensus on top? So we don't. So here so let's go back to. Right. So here, when we create a single actor, that's a single source of mutable state, and then all tasks that are invoked on, or methods that are invoked on that actor are scheduled on that actor process and executed serially. So so that avoids the distributed consensus problem. And you can, of course, create multiple actors and have multiple methods being invoked on them in parallel, but for a single actor, there are no consensus problems.
Yeah, outstanding work. I just have a quick question. When you talk about the object store, is that a replica across the instance, or is the distributed store?
So there's one object store process on each machine, and so individual objects, you can think of an object as like a partition of an RDD. It's not divided into multiple pieces. It lives on in a single object store, and if it's needed on another machine, it's copied to the other machine. The entire, the collection of object stores form a distributed process, but each individual object store is a standalone key value store.
All right, that will be the last question for the day. I'm sorry.
Hi, thanks for the presentation. The way you described it, it appears to be a framework for parallelizing and detecting dependencies between nodes. What about data operations like aggregations and joins, kind of things that a typical SQL user would think about, and Spark provides excellent support for?
Right. So the question is, what about aggregations and joins and higher level operations, right? So the API that we're exposing here is, so it's not in contrast with Spark has more of a collections-based API, and this is about individual tasks and objects. We'd like to, I mean, if we were to do that here, provide collections, it would be implemented in terms of this lower level API, but right now we don't have, we haven't implemented collections on top of Ray.
All right, well, thank you, Robert and Philip, again. Please join me in thanking them.